dark matter. In 1933, Fritz Zwicky observes galaxies within the Coma cluster moving at speeds that cannot be explained by visible matter alone, coining the term Dunkel Materie, or dark matter. Modern surveys confirm his suspicion, showing that galaxies rotate at such velocities that they should tear themselves apart unless hidden mass exerts gravitational force. This invisible substance now accounts for roughly 85% of the universe's mass, yet remains undetectable through direct measurement. Astronomers infer its presence through gravitational lensing, where distant starlight bends around massive clusters, and through discrepancies in cosmic microwave background maps. Despite more than 90 years of study, proposed candidates like weakly interacting massive particles, axions, or sterile neutrinos remain hypothetical, leaving the largest component of the universe's structure unexplained. The failure to detect dark matter directly forces astrophysics to rely on indirect evidence, pushing researchers toward even stranger theories of hidden particles. Dark energy. In 1998, two independent supernova surveys, the Supernova Cosmology Project and the High-Z Supernova Search Team, record distant Type Ia supernovae dimmer than expected, revealing that the expansion of the universe is accelerating rather than slowing. This phenomenon is attributed to dark energy, a force that makes up nearly 68% of the total cosmic energy budget. Current measurements, including those from the Planck satellite, calculate the Hubble constant at about 74 kilometers per second per megaparsec, showing how rapidly space itself stretches. Gravity, which once appeared to dominate, cannot counter this repulsive effect, leaving galaxies destined to drift farther apart with time. Some theorists even predict a Big Rip scenario in 20 to 30 billion years, when galaxies, stars, planets, and eventually atomic structures are torn apart by runaway expansion. Cosmic void. In 1981, Robert Kirshner and his team map redshifts across a wide region of sky and uncover an astonishing gap, the Boat's void, an expanse measuring nearly 330 million light-years across. Instead of the millions of galaxies expected in such a volume, astronomers count only a few thousand, revealing one of the most underpopulated zones in the observable universe. This emptiness demonstrates that matter is not evenly spread, but rather arranged in a cosmic web of filaments, walls, and voids. The discovery forces a revision of large-scale structure models, showing that gravitational clustering and dark matter distribution create enormous regions of near-nothingness. Some cosmologists even question whether the void challenges the principle of cosmic uniformity, which assumes the universe is roughly the same in all directions on large scales. Sagittarius A. At the very center of the Milky Way, 26,700 light-years from Earth, astronomers confirm the presence of a supermassive black hole known as Sagittarius A. Measurements of stellar orbits, especially the star S2 tracked for over 16 years by Andrea Ghez and Reinhard Genzel, reveal a central object with a mass of about 4.3 million suns. In 2022, the Event Horizon Telescope collaboration releases the first direct image of this black hole's shadow, confirming decades of inference. Observations also show S2 racing around the black hole at nearly 7,650 kilometers per second, a velocity that demonstrates the immense gravitational well. Occasionally, Sagittarius A flares up to 30 times brighter than its normal X-ray baseline, an unpredictable phenomenon that continues to puzzle astrophysicists. Galactic cannibalism. The Andromeda Galaxy, located 2.5 million light-years away, is currently moving toward the Milky Way at a speed of about 110 kilometers per second, confirmed through Doppler shift measurements of its stars. Astronomers project a direct collision in roughly 4 to 5 billion years, a process that will merge both galaxies into a single elliptical system. Past mergers show that such collisions ignite bursts of new star formation while simultaneously funneling gas into central black holes, triggering active galactic nuclei. Evidence of this cannibalistic behavior is already visible in our own halo, where streams of disrupted dwarf galaxies such as the Sagittarius dwarf are being torn apart and assimilated. Galactic cannibalism is now recognized as a dominant process shaping cosmic evolution, where larger galaxies grow at the expense of smaller ones. Rogue planets. Surveys in 2011 using gravitational microlensing techniques, particularly with data from the MOA and OGLE collaborations, detect a population of free-floating planets drifting unbound through the Milky Way. Estimates suggest that these rogue worlds could number in the billions, possibly even outnumbering stars by a ratio of 2 to 1. Such planets likely form within young systems before being ejected by gravitational interactions, leaving them to wander indefinitely through interstellar space. Despite lacking a host star, some may still sustain subsurface oceans warmed by geothermal heat, raising questions about habitability in environments once considered sterile. Their abundance challenges traditional definitions of planetary systems, expanding the scope of where life and chemistry might persist beyond the reach of starlight. Cosmic rays. In 1912, Austrian physicist Victor Hess ascends in a balloon more than 5 kilometers above Earth and record rising radiation levels, marking the first detection of cosmic rays. These ultra-high energy particles, often protons or heavier nuclei, strike Earth's atmosphere at nearly the speed of light and trigger vast cascades of secondary particles. The most extreme ever recorded, dubbed the "Oh my God" particle in 1991, carried an energy of 3.2 times 10 raised to the power of 20 electron volts, equivalent to a fast-pitched baseball compressed into a single proton. Their true accelerators remain uncertain, though candidates include supernova remnants, active galactic nuclei, and gamma-ray burst engines. The Pierre Auger Observatory in Argentina continues to map these showers across 3,000 square kilometers, narrowing the origins but leaving open fundamental questions about their sources. Fast radio bursts. In 2007, analysis of archival data from the Parkes Radio Telescope in Australia reveals the first fast radio burst, a millisecond-long pulse of radio energy from billions of light-years away. Each FRB releases as much energy in a fraction of a second as the sun emits in an entire day, making them among the most powerful transient events detected. Some sources repeat over time, while others appear only once, suggesting multiple mechanisms behind their origin. Magnetar's highly magnetized neutron stars have been linked to certain bursts, but many remain unexplained, leaving room for competing theories. Since 2019, the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, has catalogued thousands of FRBs, providing the most comprehensive dataset yet, but still without a definitive explanation. Black hole jets. Observations of galaxies such as M87 and Centaurus A reveal black holes launching relativistic jets that eject matter at up to 99% the speed of light. These colossal streams, powered by magnetic fields twisting at the edge of the event horizon, can extend millions of light-years into intergalactic space. The jets emit strongly in radio, X-ray, and gamma wavelengths, allowing astronomers to trace their structures across enormous distances. In 2019, the Event Horizon Telescope collaboration not only imaged the shadow of M87, but also resolved the jet emerging from its core, confirming decades of theoretical models. Such jets redistribute energy and matter across galactic scales, influencing star formation and altering the intergalactic medium itself. Cosmic background. In 1965, Arno Penzias and Robert Wilson, working at Bell Labs, accidentally detect excess microwave noise that turns out to be the cosmic microwave background, the relic radiation of the Big Bang. This faint glow fills the entire sky at a temperature of 2.725 Kelvin, offering a snapshot of the universe just 380,000 years after its birth, 13.8 billion years ago. Later missions such as COBE in 1989, WMAP in 2001, and Planck in 2009 map tiny fluctuations in the background, showing the seeds of galaxies formed through gravitational clumping. These patterns confirm the theory of early cosmic inflation, where the universe expanded exponentially within a fraction of a second. Yet, anomalies like the so-called cold spot, a region significantly cooler than models predict, remain unexplained and continue to challenge cosmologists. Great Attractor. Measurements of galactic motion show the Milky Way, along with thousands of neighboring galaxies, being pulled at nearly 600 kilometers per second toward a massive unseen region known as the Great Attractor. Located roughly 150 to 250 million light-years away, this gravitational anomaly lies behind the dense plane of the Milky Way, in an obscured region astronomers call the zone of avoidance. Infrared and X-ray surveys eventually reveal that much of the pole originates in the Hydra Centaurus supercluster, a vast concentration of galaxies exerting enormous gravitational influence. However, even with these surveys, the mass alone cannot fully explain the observed velocities, suggesting a significant contribution from surrounding dark matter. The Great Attractor remains only partially mapped, raising the possibility that still larger structures influence galactic flows on scales we have yet to measure. Heat death. The second law of thermodynamics predicts that entropy, the gradual increase of disorder, will eventually dominate the cosmos. In roughly 100 trillion years, star formation will cease, and the last stellar remnants will fade as nuclear fuel is exhausted. Over even longer timescales, black holes will evaporate through Hawking radiation, releasing their mass as faint particles until none remain. What follows is a universe of cold, diffuse photons and elementary particles spread so thinly that no meaningful interactions occur. This projected heat death represents the ultimate dark side ending, where time continues but structure, energy, and complexity have vanished. If you enjoyed this, I'm going to be posting a lot here. I would greatly appreciate it if you could subscribe. Thanks for watching.